So I just want to use a simple example to show why homogeneous linear equations require a certain number of independent solutions. Basically, if the order is 2 or 3 or 4, then we need 2 or 3 or 4 independent solutions of the homogeneous equation in order to construct our general solution. In general, though, nth order equations do require n independent solutions to construct the general solution, and they will have them. So let's kind of see the very simple example. Again, in the next few chapters, we're going to learn how to solve these equations in general using various techniques, but for this example, we can basically just think about things from a calculus point of view and basically see why there's two solutions to the second order equation and how we construct the general solution, and then find a solution that satisfies the initial conditions as well. So we're starting with a second order linear homogeneous equation with constant coefficients, and we've been given two initial conditions. So we want the function that satisfies the equation, y, but we also want the function to satisfy y of 0 equals 0, which means its graph goes through the point 0, 0, and y prime of 0 equals 1, which is telling us that on the graph at x equals 0, the slope of the tangent line is 1. So this is an extremely simple equation. I'm just saying the second derivative plus the first derivative has to equal 0. Well, a simple guess is just let y, or y1 if we want to call it, the first solution, be just a function that's 1. All the derivatives of this function are 0. So if we plug this into our equation, we get 0 plus 0 equals 0, which is true. And it also satisfies the first initial condition, but it doesn't satisfy the second initial condition. So just letting y1 be a constant function does satisfy our equation. So we need to find what's another function that satisfies the equation. And again, just by simply observing what we're looking for, what we're really saying is I want the second derivative to be equal to the negative of the first derivative. Well, a second derivative is just the derivative of the first derivative. So we're really just looking at an equation where our unknown is actually the derivative, y prime, and we want its derivative to be equal to the negative of itself. Well, that's easy. E to the minus x satisfies that condition. And in fact, this function e to the minus x, every time you take a derivative, all you're doing is changing the sign because of the chain rule. So we can actually let y be that, e to the minus x. And we see that at the second derivative of that's going to be e to the minus x, and the first derivative is negative e to the minus x, so those cancel and give us a 0. So we have two solutions to our second order homogeneous equation, and clearly they're linearly independent because e to the minus x is not equal to a constant times 1. So these are linearly independent solutions. Now let's see from another perspective why we get these two solutions as basically the basic two independent solutions that we can use to construct all other solutions. There's a lot of detail in here, but I just want to kind of talk about it a little bit. So again, we're starting with this equation, and again, we can basically what we can do is we can do a substitution here. Again, this isn't a technique you're learning how to do. This is just an explanation of why we need 5 solutions for a 5th order equation, why we need 10 solutions for a 10th order equation, why we need 2 solutions for a 2nd order equation. That's all we're doing. It's just explaining this. So in this example, basically what we're going to do is let's replace y prime with a new function. We'll call it u. So that now u is what we're looking for. All right. So what's the derivative of u? It's the second derivative of y. So if we make those substitutions in this equation up here and put it into differential form, du's and dx's, you can reorganize it into this separable equation. du over u plus dx equals 0. That's separable. We just integrate in x, and we get the natural log of u plus x equals a constant. But remember what u was. It was y prime. So I just plug that in. So this is what y prime has to satisfy. And we can solve this for y prime and using this kind of same thing we've seen before where we just change our symbols for our constants to make things look simpler. The basic solution here is y prime has to be some constant times e to the minus x. Again, we've already seen that that would be a solution. All right, but we've actually found this to be y prime is this k times e to the minus x. Well, this equation right here is another differential equation. It has an unknown constant k in it, but it's just a constant. So it's also a separable equation. And now y is the function we're looking for. So if we solve this for y, again, we can write it as dy minus k e to the minus x dx equals 0, separable. We integrate again. In other words, second order equation, we're integrating twice to undo all of the derivatives in the equation. And we get that y satisfies this equation. So y is y plus k times e to the minus x equals some other constant, capital C. Well, again, these constant names don't matter. So all we're really saying is, what is y? It has to have the form of a constant, we'll call it C1, plus a constant multiple of e to the minus x. If you plug this into the original equation, you'll see it will satisfy it, regardless of the values of the constants C1 and C2. So again, this confirms that our solution to our homogeneous equation is just a linear combination of those two functions we found. The function y1 is just 1. The function y2 is the function e to the minus x, just like we found just by easily looking at the equation in the last slide. Now in general, you can't do this to solve an equation. This equation I contrived it to make it easy to solve as basically solving two separable equations in a row. Most linear equations, you can't do that. But this is just an example to illustrate why we have two independent solutions. However many derivatives we have, we in some sense have to antidifferentiate that many times. And every time we antidifferentiate, we have to pick up a new arbitrary constant. So that's why an nth order equation will have n independent solutions, so that your general solution will actually have n arbitrary constants in the formula. And then we can use the initial conditions or boundary conditions to determine the exact values of those. So let's go ahead and do that next. So remember, we had this initial value problem, second order. We've already found that it's a homogeneous equation, so the solution yh, which we're calling the solution of the homogeneous problem, is our solution. We don't have to find another part of the solution. This is already a homogeneous equation. So we have our general solution right here. So all we have to do is that y is going to be this y sub h. Okay? So if I plug in 0 into this function, what do I get? I get c1 plus c2. Well, that has to equal 0. So y of 0 has to equal 0. So c1 plus c2 has to equal 0. Now when we differentiate it, our solution, which is this y sub h, and I'm calling it y at the same time, notice I'm calling them the same thing, all we get is the derivative of the constant is 0, and the derivative of this constant times e to the negative x is just negative times that. So I get negative e to the negative x. So plugging that into our initial condition, y prime of 0 equals 1, I get negative e to the 0, c2 e to the 0 has to be 1, but e to the 0 is 1. So c2 has to be equal to negative 1. So this is an example where solving these system of two equations is easy because one of the equations actually already tells us what one of the values is. That's not always going to happen. So if c2 is negative 1, we plug that into the original first equation, and then that tells us what c1 has to be. So c1 has to be 1 to make that true. So we construct our solution as 1 minus e to the negative x, just by plugging those constants in. That's why we get our solution. Again, I'm calling it y sub h because this is a homogeneous problem, but since it is a homogeneous problem and we're not concerned with solving anything more than this, this is the solution. to this initial value problem. So the general point is, when you have a linear equation of nth order, you have to find a solution to the homogeneous problem, which will have this format. It'll be a linear combination of n solutions. Each one comes with an unknown constant coefficient. And those are the coefficients that will allow us to translate the initial conditions into a system of equations so that we can solve for the exact values of those constants, C1, C2, C3, etc., etc., etc.